for all his help throughout this project, and Dr. Arpin Nima, who is sitting there, and Dr. Reshubo from UC San Diego, and the staff from the peer labs give me a lot of help in putting all these things together. So first I would love to say a little bit about the concept of resiliency. A seismic resilience system has the following characteristics. First, it has reduced failure probabilities, and second, it has reduced consequences from failures. And lastly, it needs reduced time to recovery. So schematically, the measure of the seismic resiliency is shown in the figure here. And our goal is to reduce the R. And we have two ways to achieve this. First, we can reduce T1 minus T0, which is the time needed to bring the structure back to its normal operation. And we can also reduce 100 minus Q of T, which is the loss of the infrastructural quality during the earthquakes. So in terms of the bridge seismic resilience, it means the ability of the bridge to minimize earthquake-induced damage and to minimize the function and to maintain functionality and minimize repair cost and also the downtime after moderate to strong earthquakes. So a few words about hybrid simulation. So the idea of hybrid simulation is to split the structure into two parts, the analytical part and the experimental part. The analytical substructures are generally those that can be modeled with confidence, while the experimental substructures are those that are difficult to model and maybe due to lack of prior data, due to complex geometry and boundary conditions, or because of the material inelastic behavior. So in terms of this new type of bridge bend, because we have limited data of technologies in the resilient bridges and the difficulty to test a complete bridge in a lab. So therefore hybrid simulation is a good choice for us to do during in a lab. So two different resilient bridge systems have been investigated by our group. The first one is the hybrid simulation of a V-connector, which is an innovative connecting device. And this test was completed in the year 2018. So in this test, the V-connector itself is the experimental substructure, and the rest of the bridge is simulated as the experimental substructure. And in the second system, which is the system I'm going to talk about here, so the superstructure of the bridge is treated as the experimental substructure, and the two-column bridge bend is being tested as the experimental substructure in the lab. So a few words about the innovative design features. So first, it has the self-centering capacities, and the self-centering is provided by the PT bars inside the column. And second, it has a steel jacket outside the column. So the steel jacket can be treated as both the formwork, and it can also be served as the transverse reinforcement to provide confinement. And third, it has energy dissipation, and the energy dissipation is provided by the mild steel inside the columns. And lastly, the rocking behavior is allowed at the beam column interfaces. Before doing the hybrid simulation, a shaking table test was conducted by UC San Diego in the peer lab in 2017. So the test specimen represents a 35% scale specimen with two-column bridge bend representing an existing California hybrid bridge. And the inertia force was simulated by 6 mass blocks attached to the top of the specimen, and they did a total number of 12 ground motions, and each ground motion has one horizontal component and one vertical component. And the test was conducted in the Pier 6 degree of freedom shaking table enrichment field station. So in phase 1 of our hybrid simulation, so the mass blocks were removed and replaced by the analytical mass modeled in the computer. So, and our goal in the phase 1 is to compare the results from the hybrid simulation against the results from the shaking table test. And here is the test setup. And we have a horizontal actuator that applies the horizontal displacement. And this is because from the shaking table test results, we found that the top moment at the cat beam level is negligible, so that's why we decided to apply only the displacement instead of applying both the displacement and the moment. And to consider the variation of forces caused by the vertical ground motions, we have another vertical actuator that applies the gravity load and the force caused by the vertical ground motions. And the lateral supports, the outer plane restraint was provided by welding the T-beam to the steel plate embedded inside the cat beam, so that in this case the cat beam can move together with the T-beam on the lateral support system. So in phase 1, the response from two directions was represented by two independent and uncoupled differential equations. So meaning that the horizontal and the vertical DOFs are separately formulated. So the damping coefficient C1 and C2 were estimated from the shaking table test. Here is the new developed hybrid simulation system and its components. So here, two uncoupled single degree of freedom equations were numerically solved using MATLAB Simulink computational platform. And after the displacement has been solved, the computed displacements needs to undergo interpolation, and then it was sent to the controller after the digital to analog conversion. And after applying the computed displacements to the specimen, so the corresponding resisting force was measured by the load cells inside the actuator, and then the analog voltages representing the force were converted to digital force values before they were passed on to the time-stepping integration algorithm to move our solution to the next time step. And in addition, a data acquisition system was used to collect data from different experimental instrumentations. So the computational platform of MATLAB Simulink has two tasks. First, it does the numerical integration by the MATLAB function block, and the explicit Newmark integration algorithm was implemented inside this MATLAB function block. And the second task is to perform the displacement interpolation between two adjacent time steps. This is because we want to avoid sudden application of large displacement commands. So before starting the hybrid simulation, a gravity load of 47 kips representing the 6 mass blocks was applied. So from the figure on the left, we see that during the gravity loading phase, so there are two different slopes. So this was caused by the small gap between the vertical actuator top clevis and the surface of the cat beam. So shown on the right. So when the vertical actuator pulls down, it first tries to close the gap between the clevis and the cat beam. So therefore, the stiffness at this stage is very small. And after the gap has been closed, the actuator starts acting against the specimen and the response becomes much stiffer. So this is one of the limitations in the setup, and this is because when we apply the displacements, we need to make sure that the measured force are correct. But in this case, the measured force from the vertical direction is not correct. So that's why we decided to switch from displacement control to force control in the vertical direction. And the vertical force was obtained by multiplying the specimen stiffness in the vertical direction with the calculated vertical displacement to obtain the vertical force. So the first 6 ground motions that were previously used in the shaking table test were used in the hybrid simulation. The results from earthquake 3, 5, and 7 will be presented in the following. So here are the results from earthquake 3. So basically here are just some part of the comparison. So here I show the comparison in terms of the horizontal displacement, the horizontal force, the acceleration, and the hysteretic behavior. And this slide shows the results from earthquake 5. And this is the result from earthquake 7. So from these 3 slides, we see that the hybrid simulation and the shaking table test results, they match quite well, which is to be expected. And this comparison and the verification will increase our confidence on the application of hybrid simulation in the structural engineering community. And in the second phase, the bridge band is simulated as the experimental substructure, and we incorporate the full bridge to study the system level performance of the bridge. So in terms of the bridge deck modeling, so the top figures shows the subdivision of the bridge deck into n equal length elements. So the element coordinate system was chosen such that they coincide with the global coordinate system. In this case, we don't need any coordinate transformation. And in order to formulate the stiffness matrix, the direct stiffness implementation method was used. And another thing is that the consistent mass matrix was employed in this case. So for the abutment, we choose the C-type abutment, and the simplified abutment modeling was selected. According to Caltrans SDC, the force displacement backbone curve in the longitudinal direction is shown on the right. And the stiffness and the strength are given by the following expressions. So here the abutment height and width were obtained from the prototype bridge geometry. And we select this jack tunnel rollover crossing as our prototype bridge. And the gap distance was chosen to be 1 inch. And the wall in the transverse direction, the wall effectiveness coefficient and the participation coefficient were taken into consideration. So from the previous slide, we use 3 nonlinear springs at each end of the bridge deck. So in the longitudinal direction, so a compression-only spring with an elastic, perfectly plastic gap material was used to represent the abutment back wall. And in the transverse, a spring with an elastic, perfectly plastic material was used to represent the backfill, the wing wall, and the power system. And in the vertical direction, a compression-only elastic spring was used to represent the bearing pad. And in formulating the equation of motion, the resisting forces from the abutment were added to the global resisting force vector after performing the state determination. So this slide shows results from one test run in the system level testing. So basically we repeat earthquake 7 on the full bridge system. And here are some observations. So the first observation is that the period elongation is quite obvious, and this is to be expected because we are switching from a bridge band to the full bridge system. And the second observation is that, so in the system level testing, even if the specimen undergoes smaller peak displacement, but it has larger residual displacement. And the third observation is that the transverse abutment undergoes significant yielding during the full bridge testing. Another thing we did is that we select 3 ground motions representing the service level, the design-based level, and the maximum considered earthquakes according to the target spectrum. And we run these ground motions one after another to investigate the system level response. And again, we observe the larger displacements, the residual displacements at the end. And we see that the transverse abutment has significant yielding. The residual drift ratio is about 1.2%, which is much larger than the residual drift observed in phase 1. And in order to explain the larger residual displacements at the end of the motion, a parametric study was considered to investigate the effect of the abutment on the behavior of the full bridge. So to do this, the bridge band is modeled using a zero-length spring whose hysteretic behavior is calibrated against.
I know we are running to the break, but certainly we have time for a couple of questions.
Yeah.
So when you modeled the transverse abutment response, so the shear keys pretty much, did you take into account that small gap that is there?
No, in the transverse direction we didn't.
No.
We only take into consideration the gap in the longitudinal direction.
Okay. And did you actually model the entire kind of backbone curve of or the behavior of the shear key, including the fracture or the failure of the shear key, or did you have it just kind of as a elastic, completely plastic?
So you mean in the transverse or in the
Yeah,
longitudinal?
in the transverse.
In the transverse, the material behavior we use is the elastic, perfectly plastic
Okay.
material. Yeah.
One more.
It's the same
Same
question.
question,
Sure,
right.
yeah.
Even better. All right, so since we've kind of run into our break already, I want to again thank all our speakers first.